Okay, we defined a lot of things towards the end of the last lecture. Let me recall them and then we will do all the connections in the rest of the lecture. Okay, so given G, we had this notion of perfect elimination ordering. Also called PO or sometimes simplicial ordering. Of the vertices is an ordering of the vertices such that, let us define this word which I did not, predecessor of Vi is neighborhood of Vi, open neighborhood of Vi intersection V1, V2, Vi minus 1 induces a clique for so given a graph we call an ordering of the vertices as a perfect elimination ordering or a simplicial ordering. If it is true that if you take the ith vertex and look at all its neighbors before, they should induce a clique. Okay. So, in fact, so not every graph may have an perfect elimination ordering. We are going to look at graphs that have such an ordering. Okay. So, this is one notion we saw. Let me also, I am not sure I defined this as simplicial vertex. Is a vertex whose neighborhood induces a clique. Clearly, if the graph has a perfect elimination ordering, it should have a simplicial vertex, right? Why? So, we are going to call this PO. Why is this true? The last vertex, yeah, because for a simplicial ordering, all we want is the neighbors before induce a clique. For a simplicial vertex, you want all its neighbors to induce a clique. Take the last vertex in the induced simplicial ordering, its neighbors is the neighbors before, and so they are the simplicial vertex. Okay. Okay, and then what are other notions? G is chordal. This is a definition. For every cycle, is what is called a chord. It's an edge that joins two non-adjacent vertices of the cycle. Okay. Okay, and then all of this is towards looking at tree with k as a different in a different way. So that was my goal, right? So that I defined the notion of a k tree. G is a k tree. Again, definition. Okay. If it has a simplicial ordering, so I don't know, I might have not been stated this definition correctly last time, but this is the definition. It has a simplicial ordering of its vertices such that the size of predecessor of Vi this is a more cleaner way of saying. So, what am I saying? That it has a simplicial ordering. What that means that for every vertex, you look at the predecessors, they induce a clique. Now, I'm also now insisting how many predecessors it should have. I want everybody to have k predecessors. Okay, but the initial vertices may not even have k guys before. So, whatever number of predecessors they have, just put that in. So, if you have k, you should have k. If you don't even have k before you, then whatever number before you, put that many predecessors I should have. So, now this is more or less what I described. So, if how does it look like? The first k plus 1 vertices form a clique, right? Is the definition clear? That is the definition of simplicial ordering. By simplicial ordering itself means that induces a clique. That is my definition. I am defining it that way. I said last time what I defined, forget that. I might not have said that correctly. This is the definition I am going to use. So, this is my definition. So, what I am saying is, so first k plus 1 vertices form a clique. Now, after that, so it is V1, V2 up to Vk plus 1, they form a k plus 1 clique. After that, for any other Vi, you pick some ki vertices that is already forming a clique and then make it adjacent to that, some k vertices. So, I always choose some k vertices that actually induces a clique. But I am going to define, partial k tree. So, this is just for convenience, this very strict definition, but here I am going to loosen things. If it is a subgraph of a k tree. Okay, so that means its neighbors need not be clique and all that. So, I have just loosened the whole thing, right, because I have just again subgraph means I can just delete some edges. Okay, so now two things we want, okay, well, three things we wanted to say. First of all, why do I care about perfect elimination ordering? What good does it do? I will show that if a graph has a perfect elimination ordering, then the clique problem, independent set problem, vertex cover, coloring, all of them can be solved in polynomial time. Okay. So, a graph having perfect elimination ordering is so special that problems that are NP hard in general graphs, some of them can be solved in polynomial time. In fact, even linear time. So, what is the use of, right? So, if G has, so here are some theorems we will see. Click, independent set, coloring, vertex cover. Then I am going to say that, well, the graphs having perfect elimination ordering are exactly caudal graphs. Then we will see that these are sort of independent statements, but we will find some connection. G has tree width at most k if and only if G is a partial K2. This is really the goal I was aiming at, to give another perception of bounded tree width graphs. Okay, so we will actually see this. This direction we have already seen. If G has a perfect elimination, we'll see both. Okay, we'll go through all of them. Okay, and then let me also just use this chance to introduce you some special subclasses of caudal graphs, which are again very well studied. Split graphs. So, what is a split graph? You can partition the vertex set into two parts. One induces a clique and the other induces an independent set. Okay, so it essentially looks like this. So, this is a clique part, this is an independent set, and you can have any kind of edges across. So, split graphs are caudal. Is that easy to see? Well, okay, so you are using this characterization and you want to give a perfect elimination ordering. So, what you are saying is, if you can partition the vertex set like this, I will number them as 1, 2, 3 up to whatever k size of the clique, and then put the remaining vertices in any order you like. You know that for every vertex, its previous neighbors in the previous set forms a clique, right, because here that is true, and for every vertex the neighbors are only this side and any subset of them induces a clique. That is one way to see it if you use this characterization. But if you simply use the definition of a caudal graph, you do not have a large induced cycle, right. How will you get a large induced cycle? Well, since this is an independent set, say let us say if you have a cycle of length 4, it has to, this is my independent set and clique, it has to start here, and suppose it is chordless, right. So, I don't know. So, I can have the next edge go here, then the next edge has to be like this, but then there is this chord because it is a click. Okay. So, if the next edge goes here. So, the next edge may be going here, then where is, because this is independent. So, it has to come here, then you have a chord. Okay. So, you can show by some case analysis that you can't have a large chordless cycle, but you know, this is a very nice characterization which you can use, that you can give a perfect elimination order. So, this is a very special class of chordal graphs, which is also very well studied. Interval graphs. So, what you do is, you suppose take a bunch of intervals, closed intervals in a real line. So, here is my real line. So, here is an interval, here is an interval, maybe here is an interval. So, these intervals I am going to call this as A, B, C, D, E. Now, from these intervals I will come up with a graph where the vertex corresponds to an interval and I draw an edge between a pair of points if these two intervals intersect. Okay. So, that is an interval graph. It is an intersection of, it is an intersection graph of a collection of intervals. So, I will just write it like this, but intersection graph So, is it easy to see that that is chordal, right? So, let us say I have a cycle of length 4, then this A corresponds to an interval, you know, let us say this is my interval A, then B corresponds to an interval that intersects with A. So, let us say that is my B, C corresponds with, intersects with C, but not with A. So, that is my interval, and D intersects with A and C. I cannot have an interval that intersects with A and C, but that does not intersect with B. So, if I draw in any way, it will mean that I have a chord TB. Okay, and this is not, this is just an example, but one can prove formally that every interval graph is a chordal graph, because you cannot have a chordless cycle large length. Okay, one interesting challenging question about these class of graphs is, okay, for all of these class of graphs you can solve many hard problems polynomial time, because they are all chordal and you have perfect elimination. By this theorem one you can solve this. So, that is why one studies these kind of graphs. But an important question is, how do you recognize these graphs? Given a graph, how will you know whether it is chordal, how do you know whether it is split, how do you know whether it is interval graph, you know? They are usually not very easy, but again well studied. There is a whole, there is another graph, let me just say that and stop my rambling on this and I will get to these theorems. There is a whole class of graphs called perfect graphs. What are these graphs? G is perfect if for every induced subgraph omega of G is equal to chi of G. What are these notations? This is the max click size, sorry, H. And this is the minimum number of colors required, a chromatic number. If this happens for every induced subgraph of the graph, then such a graph is called perfect. And interval, split, chordal, all of these graphs are perfect graphs. They are also very well studied, much more complex structure than chordal graphs, where also some of these problems can be solved in polynomial time. But that polynomial time algorithms use some linear programming and polytope theory and so on. But at least in the process of proving theorem 1, we will see that chordal graphs are perfect. Bipartite graphs are perfect, right? Can you see that? Yeah, bipartite graphs cannot have a large clique. Their chromatic number is 2. If you take any induced subgraph of bipartite graph, if you have an edge at all, then its chromatic number is 2 and click size is 2. Otherwise, it's 1. Right? So bipartite graphs are perfect. But bipartite graphs are not chordal, need not be chordal. Okay, so let me just say, so there is bipartite. Some bipartite graphs are chordal, and they all belong to this perfect class. And within chordal is my interval, split. I don't offhand recall the connection between them, whether any one. I think these are all independent. They may have some intersection. Okay, so there's a whole book. I mean, actually, several books on. There's a book by Golumbik on perfect graphs, Martin Golumbik, and then there is another book, Graph Classes. I forget the name of the author. Maybe next time I'll mention. There are a lot of work on a whole lot of graph classes, recognizing them, and hard, polynomial time algorithms on those problems, some structure about these problems. Forbidden characterization, right? You can define these classes as a graph is split if and only if it does not have the following graphs as a forbidden subgraph. So these are forbidden graph characterization of these class of graphs, and they've not been very well studied. There's a whole rich set of work on these graph classes if somebody is interested to explore. Okay, in the rest of the lecture, I'm going to prove these 3 theorems. Okay, so if you have a perfect elimination ordering, okay, I may not show all the problems, but I'll give you a flavor of. So G has, so V1, V2 up to Vn is a perfect elimination ordering of the vertices of G. I want to solve the clique problem, right? So we know that the max clique size of G, every vertex, its predecessors induce a clique. So including that vertex, that is a clique, right? So we know that it is at least, let me say, max right? Agreed? Because by definition, if you take Vi, if you look at its predecessors, right, they induce a click. So, that plus this is a click in the graph. So, the max click will be at least. So, now I run this, I compute this quantity, number of predecessors plus 1 for every vertex, given a perfect elimination ordering, take the max of it, that is clearly a lower bound for the max click size, and I want to claim that that is the maximum you can get. You cannot really get more than that. Okay, so then it's a very simple linear time algorithm once you have the perfect elimination ordering to find the max click. Is that easy to see? Yeah, right. The claim is if k is a max click, then size of k must be equal to how do I show? Yeah. So, take your vertex set of k, look at the last vertex in the perfect elimination ordering, its predecessors form a clique. So, you can even say it cannot be more. So, you can say so, right. So, the last I have this V1, V2 up to Vn, and let us say my clique contains some k vertices out of this. I take the last vertex here, then this set of vertices I picked is a subset of its neighbors, right. So, and so its predecessor is exactly all its neighbors in this set. So, max of this is at most at least k, so it follows. Okay, and coloring is also pretty easy. So, again essentially you are doing some sort of a greedy thing and it works. So, how do you want to coloring, right? So, color V1 with color number 1 for I equal to 2 to n, color Vi with minimum possible color, which means you look at your neighbors who have been already minimum possible color. Yeah, I know what I am trying to say, right. So, I look at Vi, so I will color it from V1 to Vn, I come to Vi and I look at all my neighbors before and look at their colors and then pick the smallest color available to me, avoiding that, color it with that color. Okay. So, Vi has some vertices coming later, I am not bothered about it, look at those vertices that have come before, because those are the ones that have been colored. Among all those that have been colored, pick the color which is freely available to me, which just avoids those colors which have been used among my neighbors. Okay. Then how many colors do I need? I actually need exactly this color, this many colors, because it's maximum, at most I need at most predecessor I plus 1 colors, because that's the number of colors used by my predecessor. So, number of colors used but that many colors is required. Why? Because there is a clique of that size. So that's the minimum coloring. Okay, so I'm using at most this many colors, and this many colors is necessary because there is a clique of this size. Click coloring. Okay, independent set. If I solve independent set, I can solve vertex cover, right? Because it's complement. So independent set. It is tempting to do something like a greedy, but Ashwin is saying no. It doesn't work. Okay, good question. So why I could take a complement graph and find the max click. What's the problem with that? The complement may not be caudal, right? So that's a useful thing to notice. If a graph is a split graph, its complement is a split graph. That's very easy because independent set and a click, the independent set will become a click, this will become an independent set. But if a graph is caudal, it's not necessarily true that its complement is caudal. So that doesn't work. Right? I can't find its complement graph and find it click. No, I was going to suggest maybe I do a greedy that I pick V1 into my solution and then avoid all its neighbors and pick the next available vertex into my solution and keep doing it. Okay. Yeah, unfortunately that doesn't work. So look at this graph. This is a perfect elimination ordering because in all neighbors before a click. If I pick V1 into my solution, that's it. I can't pick anything else, and this is not a max independent set. But what works is if you go in the other direction. Okay, so yeah, that's what I mean. The other direction. Start with the so my independent set contains Vn, and then I'm going to say for I going from n minus down to 1, pick Vi in I if Vi has no neighbors in I. So this is a right, so start with Vn included into my solution, and then I just keep moving in that direction. Pick the next vertex which doesn't have any neighbor to whatever I have picked and include it in my solution. So how do you show that this gives you the maximum dependency? Okay, so I'm going to leave this as an exercise. So we can show that Vn is always in the maximum independent set. In fact, in our maximum independent set. So can we at least argue that without loss of generality, Vn will be in any maximum independent set? Okay, that's easy to argue. Thing. Yeah. So, suppose not, right? Suppose the last vertex in a maximum independent set is some Vk or something. Then
All these are neighbors of Vk.
why?
Sum of
So, what happens if I just remove Vk and add Vn? Okay, let's. Yeah. So if Vn was adjacent to Vk, okay, Vn is not adjacent to Vk, can I add Vn? What am I trying to say? So show first Vn is in some maximum. So what stops me from adding Vn into my solution? Okay. Um, hmm? Okay, so suppose V1, Vn and Vk are adjacent. Okay, there are two cases. If Vn and Vk are adjacent, I claim that I can just get rid of Vk and include Vn. I will get an independent set of the same size. Why is it an independent set? Well, why may not, I mean, why should it not be an independent set? Well, because maybe V1, Vn was adjacent to some other vertex here, which is in the independent set, and so I have a problem. But then Vk should have been also adjacent to that, because remember the predecessors of Vn form a clique. Predecessors of Vn form a clique, and Vn is adjacent to Vk. So that means all the neighbors of Vn, Vk should also be adjacent, right. Since this vertex was in the independent set and Vk was not adjacent, so Vn is also not adjacent. So I can safely remove Vk and add Vn into my solution, if there is an HVn Vk. Again, is it clear? So if Vn Vk was an H, then yeah, I'm yeah, Vk, suppose not, and let Vk be the last vertex in an MIS, let us call it I. Then I claim, okay, then there are two cases. Maybe there is no two cases. I'm just figuring out online. If Vn Vk is an H, then I minus Vk union Vn is independent. Why? Because if Vn had an H to some vertex of I minus Vk, then because of this H, Vk should also have that H, but you said it was an independent set initially, so this is not possible. Okay. If Vn Vk is not an H, then
neighborhood of Vn intersection I, maximum indices.
Same argument goes through. I just do the same thing.
Because if any Vi vertex was there in the independent set
Hmm.
and before Vk,
Yeah.
then if Vn does not have an edge, then simply if Vn does have an edge,
Hmm.
then again you can delete Vi and include Vn.
Ah. Oh, you mean the earlier argument? Okay. So
Take the maximum index one, and the neighborhood intersection I.
okay. So I'll leave it here. Okay, I'm going to let you fill this up. So you can solve independent set in polynomial time, and hence you can solve vertex cover in polynomial time. So that completes theorem 1 after you do this exercise. I see. So what you are saying, maybe a simpler way of saying is, I will include Vn and delete the smallest vertex in I to which it has an edge, or the largest vertex. The largest vertex in I that has an edge from Vn, because we already argued if such a thing exists, then you can delete that and add this, that is independent. Yeah, I think that is it. So that still shows that you can safely include Vn, and then you need some sort of an induction to argue that this algorithm actually produces a max independent set.
Instead of Vn, you can have at most one adjacent vertex to that independent set. Because if it has two adjacent vertices, then I
Sure. Okay. Or maybe none. If it's none, you could have included it. Yeah. So Vn has exactly one. So include Vn and remove that. Okay. All right. Let's move on. Okay, so this shows that perfect elimination orderings are important. How do I get the perfect elimination ordering? That's another question, right? Because if you have a perfect elimination ordering, you can use that ordering to solve all of this. At least for caudal graphs, I will show you how to get a perfect elimination ordering. But perfect elimination ordering exists only for caudal graphs anyway, so we will solve that. But the algorithm I give you may not be the most efficient algorithm. There are much faster algorithms. So one direction we have already seen, right? If you have a perfect elimination ordering, then G is caudal. Why? Because if you take a large induced cycle C and look at the last vertex let us say this was the last vertex some k in that perfect elimination ordering. So, then because of the perfect elimination ordering, you know that all its neighbors before form a clique. All the vertices of the cycle are before it, because this is the last vertex of the cycle here. So, they should form a clique. But the neighbors of k are, here is one neighbor, here is another neighbor. So, there should be an edge. Okay, so you cannot have an induced a cycle without a chord. If x and y are neighbors of C, neighbors of k in C, then xy is an edge which is a chord. Okay, so we will show the other direction. So, what I will show is that G has a simplicial vertex. Is that enough? I have to give you a simplicial ordering, but I am just saying it is enough to show that G has a simplicial vertex. Why is it enough? What? Okay. Why? Because definition, right? No chordless cycle of large length. So, what? How will I use the simplicial vertex? Put it at the end. Put it at the end. Call it Vn. So, I'll find the simplicial vertex. Call it Vn. Remove that. What you have is a chordal graph. Apply this theorem and get another simplicial vertex. Put it at the end of that smaller graph and keep going. So, you will get a simplicial vertex. Finding a okay, if I prove this, finding a simplicial vertex is just what is that? Looking at the neighborhood of every vertex. So, you will find a vertex whose neighborhood is a clique, that is it. So, in order m plus n time, you can find the simplicial vertex, run through your adjacency list or something and see whether they form a clique. I do not know, m plus n time, n square, n cubed maybe, and recurs. Okay. So, if it is chordal, you can actually get a perfect elimination ordering in naively in about n cube time, but there are faster algorithms. Okay, so this is what you are going to prove. Okay, so proof is by induction. Okay, so actually we will show something stronger because we need the stronger. So yeah, so we will show if G is not complete, it has two non-adjacent simplicial vertices. If it is complete, every vertex is simplicial anyway, so it is not a problem. Okay, it is like a tree has two leaves kind of. Okay, so the proof is by induction on number of vertices. Okay, so base case n is 1, 2 or easy. So assume true up to n, and now I have so we will bring in this notion of separator and is not complete. Let A B be non-adjacent. Okay, let S be a minimal separator of minimal AB separator. Okay, so you presumably learnt about separator when we're talking about tree width, tree decomposition. But what I'm saying is, it's a set of vertices whose removal. So G is connected. Okay, we will start with connected graph. It's a set of vertices whose removal kills all paths between A and B. Right? G minus S has no AB path. So A is in one component, B is in another component, and G minus S may have a lot of components. So let's look at. So this is my A, this is S, and there may be a lot of components here. So it's a minimal separator, so that means it's a minimal set of vertices whose removal kills all AB paths, and no subset of vertices of S is enough to kill all AB paths. So A is a component containing A, and capital B is a component containing B, and there may be other components in G minus S. Okay, so now we're going to apply induction. Right. So these are all components. So case 1. The induced subgraph on A union S is complete. So if this graph is complete, then every vertex is simplicial in this graph. In particular, A is simplicial in this graph, which also means that A is simplicial in the whole graph. Why? Because A's neighbors are only in A or S. Right? Because once you delete S, you have multiple component pieces. So if this is complete, then A is simplicial Why? Because in any complete graph, every vertex is simplicial. So in that induced subgraph on A union S, every vertex is simplicial. So A is simplicial. Now I am going one more step and saying A is not simplicial just in A union S. A is simplicial in the whole graph, because where can A's neighbors be? Only in S or A, nowhere else. Right? So I am done. My goal is to give you a simplicial vertex. Actually, no. My goal is to give you two simplicial vertices. So you have a symmetric argument on B. Okay, whatever I'm going to do it only for this side for both the cases, and the same thing will apply in the other side as well, and you will get a simplicial vertex here and simplicial vertex here. Okay, otherwise, so let's use. That means G A union S is not complete. Then by induction, it has two non-adjacent simplicial vertices. If any of them is in A, then I am done, right? By the same argument. the non-adjacent is not crucial yet. If x or y is in A, then why am I done? Because anything simplicial in A union S, if it is sitting here, it is simplicial in the whole graph, because this guy has no neighbors elsewhere except in A and S. Then that vertex so we are done. So what is the case now? We have that there are two non-adjacent simplicial vertex here, they are actually sitting in S. I want to argue that that cannot be possible in a chordal graph. Okay. So so x should have some neighbor here in A, let us call it Ax. Y should have some neighbor here, let us call it Ay. Why should such a thing exist? Because S is a minimal separator, right? If x has no neighbor here, then if I throw x out, it will continue to be separator, because it is really not killing an AB path. So x has no role in the separators, I could have thrown out x. Similarly, if y is not in any AB path, I could have thrown out y and it would still be a separator. Since it is a minimal separator, x should have some neighbor here, y should have some neighbor here. Okay. So by the same token, if I am in this case, because if the other case we are done, x should have some neighbor here, let us call this Bx. Yeah. So now look at the shortest path from x to y, where the path is, all the vertices of the path are in A. Similarly, the shortest path from x to y, where all the vertices of the path are in y, B, those two paths together will form a chordless cycle, and that would be my contradiction. So otherwise, x and y are in S, let so let Ax, Ay, Bx, By be neighbors of x and y respectively in A and B. They exist because S is minimal. Now let PA be the shortest path from x to y, where all internal vertices are in A, and similarly PB, all internal vertices are in B. Now I claim that what is the situation you have? X, y, and then there is this PA, and there is this PB. Okay, so x and y are non-adjacent, remember. So this path has at least one vertex here, maybe more. This is a chordless cycle. Why is it a chordless cycle? Well, x and y are non-adjacent. Why can't I have an edge like this? Because this is the shortest path from x to y. So, in this path there are no, from x to y there are no chords here. Similarly, there are no chords here. So, it is a chordless cycle of length at least 4, which is a contradiction. So, we have shown that if it is chordal, then there is a perfect element, there is a simplicial vertex. That is what we have shown. Because if it not, I mean, but we have shown something stronger. If it's a non-complete, it's an incomplete graph, then at least 2 non-adjacent simplicial vertices. And once you find a simplicial vertex, take that as the last vertex, delete that vertex. The remaining graph is chordal by definition because there is no large chordal cycle. Any induced subgraph of a chordal graph is chordal anyway. So, you can find the simplicial ordering and attach this. Okay, so I did mention that there are more efficient algorithms to find the perfect elimination ordering, but we may not get to them. Okay, finally, I want to show that G has tree with at most k if and only if G is a partial k tree. So, you know what a partial k tree is, you know what a graph having tree with at most k, and we want to connect both of them. So, which direction is easy? Okay, I will show this. G is a k tree implies first I will show this. This is easier to show because we have put a lot of nice restrictions on tree with k tree definition. It is very well structured, neighborhood is clique, the predecessors is exactly k and all that. So, this will be easy to show, and partial trees are subgraphs of k tree. So, they will have tree with at most k. You can use the same tree decomposition for all you k, right. Okay, so why is this? Right? So, we will give a tree decomposition where there is a bag for every node and its predecessor. For I equal to k plus 1 to n. So, remember this means that there is a simplicial ordering where my predecessor Vi right, this is the definition of a k tree. So, what I am going to give you something stronger because again we will prove by induction, and so it helps to strengthen my induction. So, I am going to give you a tree decomposition where there is a bag for every node and its predecessor. Okay, there will be one bag which will contain a vertex and all its predecessors for every vertex going from k plus 1 to n. So, where do I start? Here is a bag which has V1, V2 up to, so this is sort of my base. Okay, so this is my base and I am going to attach, as vertices are coming in, I am going to introduce a bag and I argue that the whole thing is a tree decomposition of width at most k satisfying all the properties of tree decomposition. So, so I assume that you have a tree decomposition for my graph up to I, right. For my induced subgraph on V1, V2 up to Vi. Right. I is greater than or equal to k plus 1. Now, I plus 1 comes. So, let H be the last predecessor of I plus 1. So, where am I? So, my V1, V2 up to Vi, I have created a tree decomposition, Vi plus 1 comes, and by my ordering it has exactly k neighbors, yeah, and let us say the last neighbor is some Vh, right. Now, my induction hypothesis, there is a node which contains Vh and all its predecessors. I am going to take that node and attach this bag to that. So, there exists a bag containing Vh and its predecessors. Right. So, I have this tree decomposition, maybe it is actually a, for all you care, a path tree decomposition, where here is a bag that contains Vh and all its predecessors. Now, I am going to attach to this Vi plus 1 and all its predecessors. This is my new tree decomposition, and I claim that it satisfies all I need for vertices up to Vi plus 1. Okay. So, I want to give you a bag which contains Vi plus 1 and its predecessors. Here it is. Now, I have to show that this whole thing is a tree decomposition of the graph up to Vi plus 1. Well, every vertex is included, that is the first property, no problem. Vi plus 1 is here and everything else was there before. Every edge is included, the only thing I have to care about, the edge is incident on Vi plus 1, everything else was included before, and this bag contains that. The third property is the connectivity property, right. So, how do I show that? Good point. And first of all, anything that contains Vi plus 1, I want to show that it is a connected subgraph. That is not a problem. This is the only vertex that contains Vi plus 1, so it is a connected subgraph. Now, what about these vertices, right? Because so Vi plus 1 has some vertices here, there are some old vertices, I agree, but the important thing is that this is a subset of this. What am I saying? Predecessor of Vi plus 1 is a subset of why is that? Because Vi plus 1 is adjacent to Vh and all the k neighbors adjacent they form a clique. Sorry, actually it should be the other way, right?
Predecessor of VH union VH, because VH predecessor of VH will be more.
Predecessor of Vh. Yeah, so you should of course include Vh. You are saying this. Okay, right. Why? Because yeah, actually there will be a difference of exactly 1 because of this k. So Vi plus 1 is adjacent to k vertices including Vh, right? So there is Vh and then it will be adjacent to some k minus 1 vertices here. But all the neighbors of Vi plus 1 form a clique and it is adjacent to Vh. That means all these neighbors are also adjacent to Vh. So this k minus 1 guys is a subset of the neighbors of Vh. So the guys which are adjacent to Vi plus 1 excluding Vh is a subset of predecessor of Vh. So I am adding Vh also. Okay. I mean because my Vh was chosen very cleverly, it is the last vertex adjacent to it. So anything adjacent to this is also adjacent to Vh because they form a clique. So this predecessor is exactly a subset of Vh union this, and so whatever is sitting here is sitting here. So I have not lost anything. The connectivity properties, since all these guys earlier satisfied the connectivity property, they also satisfy the connectivity property because they are just adjacent to this. Okay, so I have shown one direction that if G is a partial, I just showed that if G is a K tree, then it is tree with at most K. So partial K trees have tree with at most K because partial K trees are subgraphs of K trees. Now the last piece I want to show is if G has tree with at most K, then it is actually a subgraph of a K tree. So this will have a similar flavor. So if G has tree with at most K, then it is a subgraph of K tree. Okay, so somebody has given me a tree decomposition whose width is at most K. First, let me just fill up all possible edges. So, for example, go to every bag because the same tree decomposition can realize multiple graphs. I just add all the edges and keep that graph, and I want to show that that graph is a subgraph of a partial K tree. And we will prove this by induction on number of nodes in the tree decomposition. No, actually what am I going to show? I am going to show, we will show that there is a simplicial vertex whose degree is at most K, that is all. Then it is like the caudal graph proof, the whole thing will work, okay. So we will show G has a simplicial vertex with degree at most K, with number of predecessors at most K, right. So I am going to look at that graph that has a maximum number of edges, That means I go to every bag and fill them up, make them every bag a complete graph, and still be a tree decomposition. I want to just show that it has a simplicial vertex with degree at most k. Then, take that vertex, remove it. What you have is a graph whose tree width is at most k, and you can find the simplicial vertex and keep going. So that the existence of a simplicial vertex we will show by induction on the number of nodes in the tree decomposition. If let's call this n, if n is 1, then what does it mean? I have one node, there is a bag which at most k plus 1 vertices, right? And that's a clique because I've just made it every bag into a clique. So there is a simplicial vertex whose predecessor is at most k, right? A bag so we are done. So assume n is the number of nodes in the tree decomposition in the tree of the tree decomposition, right? So go to a leaf. So I have x, this is y, and here is my x in the tree decomposition. No, let's call this, because I've been using it, A, B, a leaf with a neighbor B. Suppose, remember my goal is to just show you a simplicial vertex with at most k predecessors. Suppose x A is contained in x B. What can I do? I want to apply induction. Just get rid of this x A. What I have is a graph with tree decomposition at most k with one less node, and then I know there is a simplicial vertex by induction. Right? So delete A and apply induction, because the graph is the same. Otherwise, what is otherwise? X A has some vertex which is not in x B. What does that mean? There exists some z in x A minus x B. Can that z be anywhere else?
It has no neighbor in because separate.
What does no neighbor in B means? B is a node in the tree decomposition in x B.
Everything.
Can the z appear anywhere else? Why not?
Because
It's decomposition, so it should be
Connectivity property of the tree decomposition tells me that if z appears somewhere else, z should appear here as well. But I assume that z is not in xb. Okay, so that means z appears. This is the only node in the whole tree decomposition. Z is there. So all neighbors of z must be here. This bag is of size at most k plus 1. We have made every bag as a clique. So z is simplicial, right? X A is the only bag all neighbors of Z are in X A, so Z is simplicial with number of predecessors at most k. note also that if you have, G is a K tree, then it is caudal. Why? So yeah, because it is a simplicial order. So what this is saying is that tree with K graphs are subgraphs of a caudal graph. Because the subgraphs of K trees, and K trees are caudal. So tree with K graphs are subgraphs of a caudal graph with the maximum clique size of at most K, because K plus 1 is the back size. Okay, so the hope is that this way of viewing a tree with K graphs may be useful, because you can think of it as a process that creates this graph. I start with the K plus 1 clique, keep adding vertices adjacent to some K size cliques, and throw away some edges. What I have is a graph with tree with at most K. Okay, so that's the point of this perspective, and they are also subgraphs of a caudal graph. Because they are subgraphs of a caudal graph, you can't assume there is a perfect elimination ordering, and you can solve all of this on partial K trees or a tree with at most K. That's why you needed all this dynamic programming algorithms. Anyway, okay, I think that's it on tree width. We'll move on to something else tomorrow.